Picture a storm so colossal, so unimaginably vast, that our entire planet would vanish inside it without a trace. Now imagine this storm isn't the fiery, swirling chaos you'd expect, but something far stranger, a chilling void so cold it shouldn't exist according to every model we have. This isn't science fiction. This is the Great Cold Spot on Jupiter, a monstrous atmospheric anomaly that's left scientists scratching their heads for years. It's a mystery wrapped in the clouds of a gas giant, defying logic and rewriting the rules of planetary science as we know them. Jupiter is already a world of extremes, a planet where storms rage for centuries, where winds scream at speeds that would shred mountains, and where the very air crackles with forces we can barely comprehend. But the Great Cold Spot, it's in a league of its own. Discovered hidden in the planet's upper atmosphere, this sprawling icy patch is unlike anything else in our solar system. It's not just cold, it's impossibly cold, a blistering paradox in a place where heat and violence dominate. How does something so frigid survive in such a hostile environment? Why hasn't Jupiter's turbulent weather torn it apart? The answers could change everything we think we know about how planets, even those beyond our solar system, behave. This is more than just a curiosity. It's a cosmic detective story, one that takes us from the first flickers of its discovery to the cutting-edge theories trying to explain its existence. Some scientists believe it's a ghost of Jupiter's auroras, a lingering scar etched by the planet's magnetic fury. Others think it might be a freakish weather phenomenon, a storm of a kind we've never seen before. What if it's something even stranger, something we haven't even imagined yet? Buckle up, because today we're diving deep into the heart of this enigma, unraveling the secrets of the Great Cold Spot and why it matters not just for Jupiter, but for our understanding of the universe itself. By the time we're done, you'll never look at gas giants the same way again. The discovery of the Great Cold Spot reads like a cosmic game of hide and seek. For centuries, astronomers had trained their telescopes on Jupiter, mesmerized by its swirling storms and chaotic beauty. Yet somehow, this colossal icy void had slipped past every observation. That changed in 2017, when a team using the Very Large Telescope in Chile noticed something peculiar. Hidden in the infrared glow of Jupiter's upper atmosphere was a sprawling dark patch, a region so cold it stood out like a shadow against the planet's fiery backdrop. At first glance, it seemed impossible. How could something so massive, stretching wider than Earth itself, have remained invisible for so long? The answer lies in the way we study Jupiter. Most observations focus on its vibrant cloud tops or the raging tempests like the Great Red Spot, which scream for attention with their violent hues. But the Great Cold Spot operates in stealth. It doesn't announce itself with swirling colors or towering storms. Instead, it lingers in the thin, high-altitude layers of the atmosphere, a silent anomaly detectable only through subtle temperature shifts. Without the advanced infrared instruments of the Very Large Telescope, this frigid giant might have stayed hidden for decades more. What's even more baffling is its stability. Jupiter's atmosphere is a maelstrom of chaos where storms collide and vanish in years, sometimes months. Yet the Great Cold Spot has persisted, defying the planet's relentless turbulence. Early measurements suggested it could be centuries old, a relic of processes we're only beginning to understand. This wasn't just a fleeting weather pattern, it was a permanent fixture, a puzzle piece that didn't fit any existing model of planetary atmospheres. Scientists were left with a burning question. What cosmic forces could carve out such a stable, icy scar on a world where nothing ever stands still? The discovery sent shockwaves through the astronomical community, not just because of what it was, but because of what it represented. Jupiter had been studied since the days of Galileo, yet it still held secrets grand enough to rewrite textbooks. The Great Cold Spot wasn't merely a curiosity, it was a wake-up call, proof that even our most familiar planetary neighbors could harbor mysteries beyond our wildest theories. As researchers scrambled to explain its origins, one thing became clear: this wasn't the end of the story. It was the first clue in a much larger enigma, one that would force us to rethink everything we thought we knew about gas giants and the forces that shape them. Jupiter's atmosphere is like a runaway engine, unstoppable, unpredictable, and fueled by forces we're still struggling to measure. Imagine a planet where the sky isn't just alive, but ferocious, where hurricanes the size of continents spin for hundreds of years, and jet streams rip through the clouds at speeds over 400 miles per hour. This isn't just weather. It's a planetary-scale tempest, a swirling ocean of hydrogen and helium with no solid ground to slow it down. And yet, amid this chaos, the Great Cold Spot persists, a quiet rebel defying the fury around it. What makes Jupiter's atmosphere so relentless? For starters, it's a world without breaks. On Earth, mountains, oceans, and even forests help dissipate storms, but Jupiter has none of that. Its atmosphere stretches tens of thousands of miles deep, blending seamlessly into layers of metallic hydrogen under crushing pressures. The planet's rapid rotation, spinning once every 10 hours, whips this gaseous soup into a frenzy, creating bands of alternating winds that clash like cosmic tidal waves. These bands, striped in shades of cream and crimson, are highways for storms, some vanishing in days while others, like the Great Red Spot, become immortal. But here's the twist: even Jupiter's most iconic storms are hot compared to their surroundings. The Great Red Spot, for example, towers above its neighbors, its churning gases glowing warmer than the icy void of the Great Cold Spot. That's what makes this frigid anomaly so bizarre. In a realm where friction and compression generate heat at every turn, how does a patch of atmosphere stay so cold? It's like finding a block of ice in the middle of a volcano, a paradox that shouldn't exist. Scientists suspect Jupiter's magnetic field plays a role. The planet's auroras, fueled by particles from its volcanic moon Io, inject energy into the upper atmosphere, creating waves of heat and cold. Some researchers think the Great Cold Spot might be a shadow of these auroras, a lingering cold pocket left behind as energy dissipates. Others propose it's a standing wave, a rare atmospheric eddy that traps cold air like a celestial whirlpool. But no theory fully explains its size, its stability, or why it's only visible in infrared. One thing's certain: Jupiter's atmosphere doesn't follow Earth's rulebook. Our weather is a gentle drizzle compared to its hurricanes, and our climate models crumble under its complexity. The Great Cold Spot isn't just a curiosity, it's a key, a clue to forces we've never accounted for in planetary science. And if we can crack its code, we might just unlock secrets that apply far beyond Jupiter, from distant exoplanets to the very laws that govern gas giants across the cosmos. The Great Cold Spot doesn't just defy expectations, it shatters them. Unlike Jupiter's other atmospheric spectacles, this isn't a storm in the traditional sense. There's no spinning vortex, no towering clouds, no violent winds tearing through its core. Instead, it's something far more enigmatic, a colossal, stagnant pocket of cold, a blistering paradox in a planet where heat and motion dominate. Picture an ice cube dropped into a boiling pot, except this ice cube doesn't melt. It lingers untouched for decades, even centuries, while the chaos of Jupiter's atmosphere rages around it. That's the Great Cold Spot, a silent, stubborn anomaly that refuses to play by the rules. What sets it apart isn't just its temperature, but its sheer unnaturalness. Most of Jupiter's atmospheric features are transient, born from collisions of wind bands or eruptions of energy that fade as quickly as they form. Even the Great Red Spot, though centuries old, is slowly shrinking, its fury gradually waning. But the Great Cold Spot, it's a fixture, a permanent scar on the planet's upper atmosphere. Infrared observations reveal it stretches up to 24,000 kilometers across, wide enough to swallow Earth twice over. Yet it doesn't budge, doesn't waver, as if anchored by some invisible force. Scientists are grappling with two burning questions. How does something so cold exist in an environment where heat is constant? And why hasn't Jupiter's turbulent weather erased it? One leading theory points to the planet's auroras. Jupiter's magnetic field is a monster, 20,000 times stronger than Earth's, and its polar lights are unlike anything in our solar system, raging rivers of charged particles that inject energy into the upper atmosphere. Some researchers suspect these auroras might be carving out the Great Cold Spot indirectly, like a cosmic air conditioner. As charged particles collide with atmospheric gases, they could create waves of energy that leave behind pockets of extreme cold, a lingering chill in the aftermath of the auroral fury. But there's another possibility: standing waves. Imagine ocean waves crashing against a cliff, creating a stationary ripple where the water seems to freeze in place. Jupiter's atmosphere might be doing something similar, with wind currents colliding in just the right way to trap a bubble of cold air, a celestial eddy that refuses to disperse. If true, it would mean the Great Cold Spot isn't just a weather anomaly, it's a topographical one, a structure as fixed as a mountain range, but made entirely of air. The implications are staggering. If Jupiter can sustain such a stable, invisible feature, what else might be hiding in plain sight? Gas giants across the universe could harbor similar mysteries: cold spots, heat islands, or structures we haven't even dreamed of yet. The Great Cold Spot isn't just a puzzle to solve. It's a window into the hidden mechanics of planetary atmospheres, a reminder that even in the most violent corners of the cosmos, there's order waiting to be uncovered. And for scientists, that's the most thrilling possibility of all. Jupiter's Great Red Spot and the Great Cold Spot couldn't be more different if they tried. One is a raging inferno of a storm, a monstrous hurricane that's been churning for centuries, its crimson swirls visible even through backyard telescopes. The other is a silent, icy void, lurking unseen until infrared eyes peeled back the layers of Jupiter's atmosphere. They're like two siblings raised in the same chaotic household, one loud and brash, the other quiet and mysterious, yet both defying expectations in their own ways. The Great Red Spot is the poster child of Jupiter's fury. A high-pressure behemoth, it's a storm where gases scream upward, heating as they rise, like a cosmic chimney belching heat into space. Its winds whip at speeds that dwarf Earth's strongest hurricanes, and its sheer size, once wide enough to swallow 3 Earths, has made it a symbol of planetary extremes. But the Great Cold Spot, it's the opposite in every sense. A low-pressure zone where air sinks, cooling dramatically as it falls, creating a pocket of cold so intense it's like a freezer dropped into a blast furnace. What's fascinating isn't just their differences, but how they coexist. Jupiter's atmosphere is a battleground of competing forces, where heat and cold, pressure and vacuum, chaos and order all vie for dominance. The Great Red Spot thrives on violence, a self-sustaining engine of turbulence. The Great Cold Spot, though, seems to defy that violence, maintaining its frigid stillness amid the storm. It's as if Jupiter is showing off, demonstrating that it can harbor not just one extreme, but two polar opposites existing side by side, a planetary demonstration of balance in the midst of bedlam. Scientists are now asking a deeper question. Are these two features connected? Could the great red spot's fury somehow fuel the cold spot's chill, or are they entirely independent phenomena? Some theories suggest the cold spot might be a downstream effect of the red spot's energy, like a shadow cast by a raging fire. Others argue they're separate players in Jupiter's atmospheric orchestra, each dancing to their own tune. One thing's clear, their coexistence challenges our understanding of how planetary atmospheres distribute energy. On Earth, heat and cold tend to balance out over time, but Jupiter laughs at that idea. Here, extremes don't just exist, they endure. This isn't just academic curiosity. If Jupiter can sustain such opposing features for centuries, what does that mean for gas giants elsewhere in the cosmos? Exoplanets with similar turbulent atmospheres might harbor their own versions of these spots, hot and cold, loud and silent, each telling a different story about the forces shaping their worlds. The Great Red Spot taught us about the power of planetary storms. The Great Cold Spot is teaching us something even more profound, that in the chaos of the universe, there's room for both fire and ice, and that sometimes the most revealing secrets come from the quietest places. Jupiter's auroras aren't just light shows, they're full-blown celestial fireworks, explosions of energy so intense they outshine Earth's northern lights by orders of magnitude. These shimmering curtains of light aren't merely pretty, they're powerhouses fueled by a relentless bombardment of charged particles from the Sun and Jupiter's hyperactive moon, Io. But here's where it gets wild. These auroras might be the puppeteers behind the Great Cold Spot's eerie persistence. Imagine a spotlight so powerful it doesn't just illuminate the stage, it reshapes the entire theater. That's the kind of influence Jupiter's auroras could be wielding over its upper atmosphere. The mechanics are as fascinating as they are complex. When charged particles from Io's volcanic plumes or the solar wind collide with Jupiter's magnetic field, they spiral toward the poles, slamming into atmospheric gases like hydrogen and helium. These collisions don't just create light, they unleash torrents of energy, heating the surrounding air to staggering temperatures. But energy, like a pendulum, swings both ways. As the auroras inject heat into the poles, they might also trigger a counterintuitive ripple effect, sending waves of cold radiating outward. Picture blowing on a hot spoonful of soup. Your breath cools the surface, even as the bowl stays warm beneath. That's the paradox scientists are exploring, a scenario where auroras, the very symbols of atmospheric heat, could be sculpting one of the coldest places in the solar system. The evidence is tantalizing. Observations from telescopes and spacecraft reveal that the Great Cold Spot hovers near the boundary of Jupiter's auroral oval, the ring-shaped zone where the lights are most intense. Its position isn't random. It's a clue, a cosmic breadcrumb suggesting a direct link. Some researchers propose that the aurora's energy doesn't just dissipate, it echoes, creating standing waves in the atmosphere that trap cold air in their troughs. These waves could act like invisible fences, corralling the frigid air into a stable, long-lasting structure. If this theory holds, it would rewrite our understanding of how planetary auroras interact with their environments, proving they're not just passive glow-ups but active shapers of atmospheric architecture. But mysteries remain. Why hasn't the cold spot drifted or dissolved under Jupiter's relentless winds? Why does it appear only in the upper atmosphere, invisible to optical telescopes? And most perplexing of all, why is it so big? If auroras are the architects, their blueprint defies conventional physics. The scale of the cold spot suggests energy transfers on a level we've never documented, a hidden dialogue between Jupiter's magnetic fury and its atmospheric chaos. This isn't just about Jupiter. If auroras can carve out such colossal features on our solar system's largest planet, what might they be doing elsewhere? Exoplanets with fierce magnetic fields and violent stellar winds could harbor their own versions of the Great Cold Spot, hidden fingerprints of auroral activity waiting to be discovered. The implications stretch beyond our solar system, hinting at universal processes we're only beginning to grasp. For scientists, that's the real thrill, not just solving Jupiter's puzzle, but uncovering a new language of planetary atmospheres, one where light and cold, chaos and order are intertwined in ways we're just starting to decipher. If there's one thing scientists thought they understood, it was the basic rules of planetary weather until Jupiter's Great Cold Spot came along and tore up the rulebook. This isn't just a gap in our knowledge, it's a yawning chasm, a glaring sign that even our most advanced atmospheric models are missing something fundamental. Picture a team of meteorologists trying to forecast a hurricane, only to realize their equations can't account for a blizzard appearing in the middle of it. That's the level of disruption we're dealing with here. Supercomputers have simulated Jupiter's atmosphere for decades, crunching numbers to replicate its storms, jet streams, and heat patterns. These models are marvels of modern science, capable of predicting the Great Red Spot's movements or the dance of cloud bands with startling accuracy. But throw the Great Cold Spot into the mix and everything falls apart. The simulations can't explain how a region so cold remains so stable, untouched by the planet's relentless turbulence. It's like dropping an ice cube into a volcano and watching it refuse to melt, a defiance of physics that leaves researchers scrambling for new explanations. One leading theory points to gravity waves, the atmospheric equivalent of ripples in a pond. On Earth, these waves form when air pushes over mountains, creating oscillations that ripple upward. Jupiter has no mountains, but its storms might be generating similar waves on a planetary scale, invisible undulations that could channel energy in unexpected ways. If these waves are strong enough, they might carve out pockets of cold air, locking them in place like a cosmic refrigeration cycle. But here's the catch. Even our most powerful simulations struggle to incorporate gravity waves at the scale Jupiter demands. The math becomes a labyrinth, a tangle of variables that no supercomputer has yet untangled. Then there's the magnetic field angle. Jupiter's magnetosphere is a beast, a roiling sea of charged particles that interacts with the atmosphere in ways we're only beginning to grasp. Some scientists speculate that magnetic forces could be tugging at the upper atmosphere, creating currents that isolate the cold spot from the surrounding chaos. It's a compelling idea, except no existing model can fully account for such a delicate balance. The magnetic field's influence is like a ghost in the machine, felt but not yet seen, leaving researchers to piece together clues from scattered data. The stakes here are astronomical. If our models can't explain Jupiter, a planet we've studied up close with probes like Juno, what hope do we have for gas giants light years away? Exoplanet hunters rely on these same models to interpret the atmospheres of distant worlds, inferring weather patterns and compositions from flickers of starlight. But if Jupiter's cold spot teaches us anything, it's that gas giants might operate on a logic we haven't even imagined yet. A planet like HD 206909b, with its searing winds and molten skies, could harbor its own version of the cold spot, a hidden quirk that upends every assumption we've made. This isn't just about rewriting textbooks, it's about humility. The Great Cold Spot is a cosmic reminder that nature always keeps a few cards close to its chest, no matter how advanced our tools become. For scientists, that's equal parts frustration and inspiration, a puzzle that refuses to be solved, yet one that promises to reveal deeper truths about the universe. And until we crack it, every gas giant we study will come with a silent question. What else are we missing? Theories about Jupiter's great cold spot read like a menu of cosmic impossibilities, each one more tantalizing than the last, yet none serving up a full explanation. Take the idea of energy sinks, for instance. Imagine tossing a stone into a pond and watching the ripples vanish not by spreading outward, but by plunging straight down, as if some invisible drain were swallowing them whole. That's the essence of this theory. Atmospheric waves, generated by Jupiter's relentless storms or magnetic fury, could be funneling their energy downward, creating pockets of intense cold where the heat simply disappears. It's as if the planet has secret trapdoors in its sky, regions where the usual rules of energy transfer don't apply. Scientists speculate these sinks might form where wind currents collide in just the right way, like intersecting highways of air that force energy to dissipate vertically instead of horizontally. But here's the catch: no one's yet figured out what could anchor these sinks so reliably, keeping them fixed in place for centuries amid Jupiter's chaos. Then there's the spin factor. Jupiter isn't just rotating, it's practically a blur, completing a full day in under 10 hours. This dizzying speed twists the atmosphere into a labyrinth of jet streams and vortices, but it might also carve out something far stranger: stable holes in the planet's heat distribution. Picture a record spinning on a turntable with scratches that make the needle jump. Jupiter's rotation could be creating similar skips in its atmospheric circulation, regions where heat fails to spread evenly, leaving behind permanent cold spots like cosmic shadows. Some models suggest these holes might align with planetary scale waves, oscillations so vast they resonate across Jupiter's entire atmosphere, locking cold air into place like a celestial vise. The math hints it's possible, but the real puzzle is why we'd see only one such spot. If rotation creates these holes, shouldn't there be dozens, even hundreds of them? The wild card in all this, Jupiter's magnetic field. It's not just strong, it's a shapeshifter, warping and flexing as the planet spins, tangling with charged particles in ways that could rewrite atmospheric physics. One fringe theory proposes that magnetic anomalies, kinks or knots in the field, might act like atmospheric refrigerators, redirecting charged particles to sap heat from specific regions. It's a stretch, but not impossible. After all, we've seen how auroras inject energy into Jupiter's poles. Could the reverse also be true? Could magnetism somehow siphon heat away, leaving behind the cold spot's icy fingerprint? What's fascinating isn't just the diversity of these theories, but how they clash. Energy sinks demand precise wind patterns. Rotation holes rely on planetary scale resonance. Magnetic refrigeration leans on unseen field distortions. Each one could explain part of the cold spot's behavior, but none can account for everything: its size, its stability, its eerie invisibility in visible light. It's like trying to solve a jigsaw puzzle where half the pieces belong to a different box, and that's the real lesson here. The great cold spot isn't just challenging our models, it's exposing how little we grasp about fluid dynamics on planetary scales. Earth's weather is child's play compared to Jupiter's atmospheric ballet, where hydrogen behaves like liquid metal, where storms outlive civilizations, and where cold isn't just the absence of heat, it's an active, almost deliberate force. Until we crack this enigma, every gas giant we study, from Saturn to distant exoplanets, comes with an asterisk. Conditions may be weirder than they appear. For scientists, that's not a frustration, it's an invitation. The cold spot isn't a dead end, it's a door, and behind it lies a new frontier of planetary science waiting to be explored. Could the great cold spot have been staring us in the face for decades, unnoticed like a cosmic chameleon blending into Jupiter's turbulent canvas? Modern telescopes may have unveiled its existence, but the real detective work begins when we comb through old mission archives, grainy images, and decades-old data that might hold the key to its origins. Take the Voyager missions of the late 1970s, humanity's first up-close glimpse of Jupiter's fury. Those iconic snapshots captured swirling storms and churning clouds, but buried in the background, obscured by the planet's glare, could the cold spot have been lurking all along? Scientists are now revisiting these vintage datasets with fresh eyes and sharper tools, hunting for thermal fingerprints that earlier instruments might have missed. Early hints suggest the anomaly could trace back to the 1990s, spotted faintly in infrared readings from the Galileo probe. But here's the twist. If the cold spot was there 30 years ago, why did it take so long to confirm its presence? The answer lies in the limitations of older technology. Early infrared sensors lacked the precision to distinguish the cold spot's subtle chill from Jupiter's background noise. It's like trying to spot a snowflake in a blizzard, possible in theory, but nearly impossible without the right lens. What's truly mind-bending is the implication of its age. If the cold spot has persisted since the 90s or even longer, it upends our understanding of atmospheric stability. Jupiter's weather operates on timescales that dwarf human lifespans, but even its most enduring storms evolve over centuries. The Great Red Spot, for instance, has shrunk by nearly 50% since the 1800s, yet the cold spot, it seems frozen in time, a relic defying erosion. Could it be older than our earliest telescopic records? Some researchers speculate it might trace back to the era of Cassini's observations in the 1600s, hidden in sketches that predate modern astronomy. This isn't just about rewriting timelines. It's about the haunting possibility that Jupiter's atmosphere operates on a hidden clock, one where certain features endure while others fade. If the cold spot has survived for centuries, what does that say about the forces sustaining it? Earth's climate shifts over decades, but Jupiter might play by different rules, with anomalies that outlast civilizations. The deeper we dig into its past, the more the cold spot feels less like a weather pattern and more like a planetary landmark, a permanent fixture in a world of chaos. And that raises a tantalizing question. What else have we overlooked? Jupiter's history is written in light and shadow, a palimpsest of observations waiting to be decoded. Every re-examined dataset, every reprocessed image could reveal another hidden marvel. The cold spot isn't just a scientific puzzle, it's a lesson in humility, reminding us that even the most familiar worlds keep secrets buried in their past. As we sift through the archives, one thing becomes clear: the universe doesn't reveal its mysteries all at once. Sometimes they're hiding in plain sight, waiting for the right moment and the right technology to be seen. Stability in Jupiter's atmosphere is as rare as a calm day in a hurricane, yet the great cold spot doesn't just endure, it thrives. While most atmospheric quirks on the gas giant vanish within months, this icy anomaly has clung to existence with the tenacity of a cosmic tattoo, unchanged in size, shape, and temperature for decades. It's as if someone hit pause on the planet's chaos, freezing one tiny patch of sky in perfect stillness. What kind of forces could possibly anchor something so fragile in a realm where even the mightiest storms dissolve? The answer might rewrite our playbook for how planetary atmospheres work. Think of Jupiter's weather as a constantly churning ocean where waves collide, merge, and vanish in the blink of an eye. The Great Red Spot, for all its fame, is shrinking. Smaller storms flicker out like matches in the wind, but the cold spot, it's more like a deep sea trench moved by the tempest above. This isn't just unusual, it's unnatural. on Earth, stable weather patterns rely on geography, mountains, valleys, and oceans that guide the flow of air. Jupiter has none of that. Its atmosphere is a featureless sea of hydrogen, with nothing to anchor a storm unless the anchor isn't physical at all. One theory suggests the cold spot might be fed by a hidden conveyor belt of energy, a cosmic recycling plant where cold air isn't just trapped but replenished. Picture a refrigerator with a broken door, constantly leaking cold air, except instead of machinery, the coolant might be Jupiter's own magnetic field. Charged particles spiraling along magnetic lines could be siphoning heat away from the upper atmosphere, creating a self-sustaining loop of chill. It's a delicate dance, one that would require perfect balance. Too much energy and the spot warms, too little and it dissipates. Yet somehow, against all odds, that balance holds. Then there's the possibility of resonance, a phenomenon where atmospheric waves sync up like perfectly timed metronomes, reinforcing each other instead of cancelling out. On Earth, we see this in rare weather patterns like the quasi-biennial oscillation, where wind directions flip like clockwork every 2 years. Jupiter's version could be far grander, with planet-sized waves locking the cold spot into place like a puzzle piece snapped into the sky. If true, it would mean the spot isn't just surviving the chaos, it's using it, turning turbulence into a stabilizing force. But here's the kicker: neither theory fully explains why the cold spot hasn't drifted. Jupiter's jet stream should have shoved it across the planet like a leaf in a gutter, yet it stays stubbornly fixed in longitude, as if glued to the atmosphere. Some scientists whisper about ghost currents, invisible flows in the upper atmosphere that act like celestial guardrails, steering the spot back into position whenever it strays. Others wonder if we're seeing the fingerprint of deeper layers, where movements far below the cloud tops ripple upward, anchoring the cold spot from realms we can't yet observe. The deeper we dig, the clearer it becomes. This isn't just a weather pattern. It's a signal, a clue that Jupiter's atmosphere operates on rules we haven't decoded. For all our probes and supercomputers, the cold spot remains a masterclass in cosmic humility, a reminder that the universe reserves its most profound lessons for those willing to question everything they think they know. And until we solve its riddle, every gas giant we discover, whether in our solar system or beyond, comes with a silent challenge. Think again. -200 degrees Celsius. That's not just cold, it's Jupiter's great cold spot cold, a temperature so extreme it would turn Earth's toughest metals brittle as glass in seconds. To put that in perspective, the average temperature around it hovers at a relatively balmy -150 degrees Celsius, making the cold spot a blistering anomaly even by gas giant standards. It's as if someone carved out a slice of deep space and wedged it into Jupiter's upper atmosphere, a frozen island in a sea of turbulence. What's baffling isn't just the cold, it's the consistency. Most planetary weather systems swing between extremes, heating and cooling with the ebb and flow of energy, but the cold spot defies this rhythm. Its temperatures remain locked in a deep freeze, barely budging even as Jupiter's storms rage around it. This isn't passive cooling, it's as if the spot has its own built-in thermostat, actively shedding heat faster than the planet can replenish it. Scientists are scrambling to explain how such a precise chill could persist without some unseen force pumping the cold like a cosmic air conditioner. The leading hypothesis: auroral refrigeration. Jupiter's auroras dump staggering amounts of energy into the poles, but that energy doesn't just vanish, it ripples outward, potentially triggering waves that suck heat from the atmosphere. Picture blowing across a steaming cup of tea. Your breath cools the surface by whisking away warmth. The cold spot might be experiencing something similar, but on a planetary scale, with aurora-driven waves acting like a celestial fan, stripping heat molecule by molecule. Yet even this theory has cracks. If auroras are the coolant, why isn't the cold spot near Jupiter's poles where the auroras are strongest? Instead, it lingers closer to the equator, a mismatch that's left researchers scratching their heads. Some speculate the spot might be a cold trap, a zone where atmospheric currents converge to funnel heat away, like a drain in a bathtub. Others wonder if exotic chemistry is at play, hydrogen compounds forming icy aerosols that reflect heat, or even rare phases of helium behaving like molecular heat sinks. The implications stretch far beyond Jupiter. If a natural refrigerator can exist in its atmosphere, why not elsewhere? Exoplanets with fierce auroras or wild magnetic fields might harbor their own cold spots, hidden quirks that skew temperature readings and baffle astronomers. The cold spot isn't just a curiosity, it's a benchmark, proof that planetary atmospheres can achieve feats our models never predicted. And until we unravel its secrets, every gas giant we study will come with a silent disclaimer: expect the unexpected. Imagine standing under a tree on a sunny day, watching the dappled shadows shift on the ground. Those dark patches aren't objects themselves, they're echoes of something real happening above. Now picture that same principle unfolding on a planetary scale, where Jupiter's great cold spot isn't the main event but a ghostly imprint of forces churning far below the clouds. This isn't just a poetic comparison, it's a serious scientific hypothesis gaining traction among researchers. If true, the cold spot could be less of a weather phenomenon and more of a cosmic shadow, a fleeting glimpse into processes occurring in realms we'll never directly observe. The logic is as elegant as it is revolutionary. Jupiter's atmosphere isn't a thin veneer. It's a crushing, churning ocean of hydrogen and helium thousands of miles deep, with layers behaving in ways that defy earthly intuition. Near the top, where we see the colorful bands and storms, temperatures are relatively manageable, but dive deeper, and things get extreme pressures so intense that hydrogen turns metallic, forming a bizarre, electrically conductive sea that fuels the planet's monstrous magnetic field. Somewhere in that abyss, colossal currents could be flowing, vast rivers of gas moving heat and energy in patterns we can't yet map. The cold spot might be their calling card, a faint signal rising to the surface like a bubble in a lava lamp. One compelling analogy comes from our own oceans. Earth's thermohaline circulation, a global conveyor belt of water driven by temperature and salinity, creates surface effects like the Gulf Stream, which shapes climate's continents away. Jupiter could have its own version, but operating on steroids, with metallic hydrogen acting like a superfluid and magnetic fields adding twists we can't yet imagine. If deep currents in this hidden layer surge upward, they might depress temperatures in the upper atmosphere, creating a localized cold zone that lingers for centuries. It's like a planetary-scale ice cube forming where a deep-sea vent chills the ocean's surface, except here, the vent is a disturbance in Jupiter's alien heart. The implications are staggering. If the cold spot is indeed a shadow, it's not just a curiosity, it's a Rosetta Stone for decoding Jupiter's interior. Normally, studying these depths is nearly impossible. Even NASA's Juno probe, which peers beneath the clouds with microwave sensors, can only scratch the surface. But the cold spot could be a natural probe, a flickering screen onto which the planet's hidden dynamics are projected. By analyzing its temperature fluctuations, size variations, or even subtle shifts in position, scientists might reverse engineer the currents below, much like seismologists use earthquake waves to map Earth's core. Yet mysteries remain. Why would these deep disturbances create such a sharply defined cold zone instead of a fuzzy blur? How does the signal traverse thousands of miles of turbulent atmosphere without dissipating? And most crucially, if the cold spot is a shadow, what's casting it? Some theorize it could be linked to Jupiter's mysterious dynamo, the engine of swirling metallic hydrogen that generates its magnetic field. Others speculate about hotspots, deep thermal plumes that indirectly birth cold patches above, like atmospheric afterimages. Whatever the answer, one thing's clear: the cold spot isn't just a feature of Jupiter's atmosphere. It might be the only visible thread in a tapestry woven deep inside the planet, a thread that, if pulled, could unravel secrets about gas giants across the cosmos. Jupiter's magnetic field isn't just strong, it's a cosmic powerhouse, a swirling labyrinth of invisible forces that could hold the key to the great cold spot's existence. Clocking in at nearly 20,000 times stronger than Earth's, this magnetic behemoth doesn't just guide compass needles, it sculpts entire swaths of the planet's atmosphere with its influence. Picture a colossal, invisible hand pressing down on Jupiter's upper layers, redirecting charged particles like cosmic billiard balls in ways that might just explain our icy enigma. Here's where things get electrifying. Jupiter's magnetosphere is crammed with high-energy particles, many siphoned from its volcanic moon Io. These particles spiral along magnetic field lines, crashing into the upper atmosphere near the poles, creating those mind-blowing auroras. But the field's reach extends far beyond the poles, creating intricate patterns of energy distribution that could be silently shaping the cold spot hundreds of miles away. Some scientists suspect these trapped particles might act like atmospheric refrigerants, stealing heat through collisions that excite molecules only to have them radiate that energy away into space. It's a bit like opening a freezer door in a hot kitchen. The cold doesn't stay contained. The magic, or rather, the physics, happens through a process called Joule heating's opposite, Joule cooling. When charged particles interact with atmospheric gases under the magnetic field's guidance, they can trigger waves that don't just dissipate heat, they actively transport it elsewhere. Imagine Jupiter's magnetic field as a network of invisible pipes, some funneling heat toward the auroras, others siphoning it away to create deep freeze zones like the cold spot. This wouldn't be a smooth process either. Turbulence in the magnetic field could create standing cold waves, like eddies in a river that trap floating leaves. But there's a catch. If magnetism is the architect, why isn't the cold spot perfectly aligned with Jupiter's magnetic poles? Instead, it sits at a peculiar mid-latitude, a misfit in the planet's electromagnetic symphony. This misalignment has led to wilder theories like magnetic anomalies buried deep in Jupiter's interior, creating localized cold wells where the field lines kink or cluster. We've seen similar quirks on Earth, where magnetic anomalies cause compass needles to swing wildly off course. On Jupiter, scaled up by orders of magnitude, such kinks could carve out atmospheric refrigerators large enough to swallow planets. The most tantalizing clue comes from Juno, NASA Jupiter probe. Its measurements reveal the planet's magnetic field is far lumpier than expected, with strange patches of intense magnetism that resemble cosmic bruises. Some of these patches coincide eerily with the cold spot's longitude, hinting at a direct link. If confirmed, it would mean we're not just looking at weather, we're seeing the fingerprints of Jupiter's internal dynamo projected onto the atmosphere, a hidden dialogue between the planet's molten core and its frozen sky. Yet for all these insights, the puzzle remains incomplete. Magnetism might explain the cold spot's chill, but not necessarily its incredible stability, or why similar spots haven't appeared elsewhere on Jupiter. It's a reminder that gas giants don't follow single variable rules. Their atmospheres are battlegrounds where gravity, rotation, chemistry, and magnetism collide in ways we're only beginning to fathom. The cold spot isn't just a product of Jupiter's magnetic field, it's a conversation between that field and everything else the planet throws at it. And until we decode that conversation, every theory, no matter how compelling, remains just one piece of a much larger cosmic crossword. Jupiter's great cold spot might seem like a one-of-a-kind marvel, but the universe loves patterns, so could it have cousins lurking on other worlds? When we scan our solar system's gas giants, we find plenty of atmospheric oddities, yet nothing quite mirrors the cold spot's eerie stillness and deep freeze. Take Saturn's north polar hexagon, for instance, a six-sided jet stream wider than two Earths, spinning like a cosmic honeycomb. It's a stunning spectacle, but where the hexagon buzzes with wind speeds over 300 miles per hour, the cold spot sits in eerie quiet, a study in contrast. Saturn's feature is all about motion, Jupiter's is about absence, a void where energy seems to vanish. Then there's Neptune's great dark spot, a storm so vast it could swallow Earth whole. Discovered by Voyager 2 in 1989, this swirling tempest was Neptune's answer to Jupiter's great red spot, except it vanished by the mid-90s, a fleeting bruise on the planet's blue canvas. Unlike Jupiter's cold spot, Neptune's dark vortex was a classic storm system, a high-pressure maelstrom churning with methane clouds. It roared, it raged, and then it dissipated, leaving behind no trace. The cold spot, by comparison, feels almost permanent, a fixture rather than a flare-up. Uranus offers another twist. In 2014, astronomers spotted a dark vortex in its atmosphere, but like Neptune's spot, it was a transient storm, not a thermal anomaly. These worlds have turbulence in spades, but none boast anything as cold or as stubbornly stable as Jupiter's enigma. Even exoplanet hunters, scanning distant gas giants for weather patterns, haven't found a match. Hot Jupiter's gas giants roasting close to their stars show wild temperature swings, but their extremes are all about scorching heat, not lingering cold. So what sets Jupiter apart? The answer might lie in its monstrous magnetic field and the unique interplay between its auroras and atmosphere. Saturn's hexagon is sculpted by wind shear. Neptune's spots are born from chaotic storms. But the cold spot, it's a byproduct of forces we're still untangling: magnetic whispers, hidden currents, maybe even echoes from Jupiter's depths. That's why scientists aren't just studying this spot. They're treating it as a Rosetta Stone for gas giant weather everywhere. If we can decode why Jupiter's cold anomaly exists and why nothing like it appears elsewhere, we might uncover universal rules for how planetary atmospheres redistribute energy, or reveal that Jupiter is the exception, a cosmic rebel playing by its own rules. For now, the cold spot stands alone, a frigid outlier in a family of storms, but that isolation makes it even more valuable. In science, the anomalies are often the keys, the data points that don't fit, the phenomena that defy explanation. They're the signposts pointing toward discoveries we haven't imagined yet. And as we keep searching the skies, who knows, maybe Jupiter's cold spot isn't as lonely as it seems. Maybe we just haven't learned how to spot its siblings waiting in the dark, silent and cold, on worlds far beyond our gaze. NASA's Juno mission has peeled back layers of Jupiter's mysteries like never before, but the great cold spot remains a tantalizing outlier, one that demands sharper eyes and smarter tools. While Juno's microwave radiometer and gravity maps have rewritten textbooks on the planet's storms and magnetic field, this icy enigma lingers just out of reach, a ghost in the machine that current instruments can't fully dissect. That's where the next generation of missions comes in, armed with technology designed to probe the cold spot's secrets with surgical precision. The European Space Agency's JUICE, Jupiter Icy Moons Explorer, might seem an unlikely candidate at first glance, given its focus on Ganymede and Europa. But tucked into its payload is a game-changer, the sub-millimeter wave instrument, capable of mapping temperature and chemistry in Jupiter's upper atmosphere with unprecedented resolution. If the cold spot has a chemical fingerprint, some exotic compound or unique aerosol acting as a refrigerant, this device could sniff it out. Even more promising is JUICE's ability to monitor Jupiter's auroras in concert with atmospheric changes, potentially catching the moment when auroral energy ripples outward to sculpt the cold spot's chill. It's a long shot, but sometimes the best discoveries come from instruments pointed at one target that accidentally reveal another. Then there's the dream of a dedicated cold spot probe, a spacecraft designed not just to observe Jupiter, but to interrogate this specific anomaly. Imagine an orbiter armed with LiDAR to map the spot's 3D structure, or a swarm of microsensors deployed like atmospheric confetti to measure turbulence at scales Juno can't touch. Scientists have floated concepts like a Jupiter climate orbiter, packing infrared spectrometers so sensitive they could trace heat flows molecule by molecule. The challenge: Jupiter's radiation belts chew through electronics like tissue paper, and the cold spot's high-altitude perch puts it squarely in the danger zone. But advances in radiation-hardened tech like the self-healing chips tested on NASA Europa Clipper could soon make such a mission feasible. The real prize, though, might lie in collaboration. Picture Juno, JUICE, and future orbiters working in tandem, their combined data painting a dynamic portrait of the cold spot across wavelengths and timescales. Juno's close passes could reveal magnetic tweaks linked to the spot's behavior, while JUICE's global scans track its interplay with auroras. Add a hypothetical future probe focused on atmospheric waves, and suddenly we'd have a trifecta of perspectives, like triangulating a whisper in a hurricane. This isn't just about solving a Jovian puzzle. Cracking the cold spot's code could redefine how we study exoplanets. If magnetic fields or deep atmospheric currents really can carve out such stable, invisible features, astronomers might need to revisit interpretations of distant gas giants' thermal maps. A hot Jupiter light years away could harbor its own hidden cold zones, skewing climate models until we learn to account for them. The next decade of exploration won't just answer questions, it'll teach us what questions we should have been asking all along. And for scientists, that's the most thrilling prospect of all, not just filling gaps in our knowledge, but discovering entirely new ones. So while the cold spot waits, silent and stubborn, our tools are evolving. From upgraded sensors to daring mission designs, the pieces are falling into place for a breakthrough. And when it comes, whether through a eureka, a moment in JUICE data, or some yet unplanned probe's revelations, it'll remind us why we explore in the first place, not just to catalog the universe's wonders, but to confront its most defiant mysteries head-on. Beneath Jupiter's swirling cloud tops lies a hidden world of weather, stacked in layers like a cosmic wedding cake, each tier operating by its own rules, its own rhythms. The Great Cold Spot might be more than just an atmospheric quirk. It could be a rare peephole into these deeper, unseen realms, a place where the planet's secrets rise to the surface. Think of it like spotting a crack in the ice of a frozen lake. That tiny fissure doesn't just hint at what's below, it reveals an entire ecosystem thriving in the depths. Jupiter's atmosphere isn't a uniform blanket. It's a dynamic, tiered system where temperatures and pressures shift dramatically with altitude. The uppermost layers, where we see the vibrant bands and storms, are just the tip of the iceberg. Below them, denser clouds of ammonia and water churn in perpetual motion, while deeper still, the hydrogen transforms into a metallic sea, conducting electricity and sculpting the planet's colossal magnetic field. The cold spot, perched high in the thin thermosphere, might be a fleeting glimpse into one of these shadowy layers, a place where colder, denser air from below occasionally bubbles up, breaching the boundary like a submarine surfacing through ice. This window theory isn't just poetic speculation. Infrared scans show the cold spot's thermal profile doesn't match its surroundings, as if it's borrowing its chill from somewhere far below. Some researchers compare it to a volcanic plume on Earth, where magma from deep within the mantle punches through the crust, carrying traces of the planet's interior to the surface. Jupiter's version could involve gravity waves, massive undulations in the atmosphere, dragging pockets of cold air upward from hidden reservoirs. If true, it would mean the cold spot isn't an isolated feature but a messenger, a whisper from layers we've never directly observed. The implications are staggering. Jupiter's interior is a black box of energy, a place where heat from the planet's formation still simmers billions of years later. How that heat moves, how it's distributed, these are mysteries that shape everything from storm formation to magnetic fields. If the cold spot is indeed a portal, studying its fluctuations could let us map Jupiter's internal weather like sonar pings in an ocean, revealing currents and eddies we never knew existed. It's a bit like diagnosing a fever by feeling someone's forehead, except here, the patient is a gas giant, and the symptom is a patch of cold older than human civilization. But there's a catch. For this theory to hold, Jupiter's atmospheric layers can't be perfectly sealed. There has to be some leak, some mechanism that lets deep cold seep upward without being scrambled by the chaos above. One possibility involves breaking waves, atmospheric disturbances so powerful they momentarily puncture the boundary between layers, like a rogue wave crashing over a ship's deck. Another idea points to magnetic portals, fleeting openings where Jupiter's field lines twist just right to funnel cold air into the upper atmosphere. Neither is proven, but both hint at a planet far more interconnected than we've assumed, its hidden layers in constant, silent dialogue. The real test will come from future missions. Probes equipped with deeper penetrating sensors could hunt for chemical tracers in the cold spot, molecules or isotopes that only form in Jupiter's abyss, hitchhiking their way to the surface. Finding them would be like stumbling upon a deep-sea creature in shallow waters, undeniable proof that the spot is a conduit to the unknown. Until then, the cold spot remains a tantalizing maybe, a crack in Jupiter's facade that might, just might, lead us to the heart of the storm. And if we're right, it won't just rewrite the story of Jupiter. It'll remind us that even the mightiest planets have leaks, and sometimes the coldest places hold the hottest secrets. The solar wind isn't just a gentle breeze, it's a supersonic barrage of charged particles, a relentless storm of protons and electrons screaming through space at nearly 1,000,000 miles per hour. When this cosmic hurricane slams into Jupiter, it doesn't just bounce off. It tangles with the planet's monstrous magnetic field, sparking auroras that could power civilizations and sending shockwaves through the upper atmosphere. And somewhere in that chaos, the great cold spot might be feeling the effects. Scientists have long known the solar wind shapes Jupiter's outer atmosphere, compressing its magnetic field like an invisible hand squeezing a balloon. But the cold spot adds a new wrinkle. Infrared observations reveal subtle changes in its size and chilliness that seem to sync up with fluctuations in solar wind intensity. When the wind blows harder, the spot might stretch wider or dip a few degrees colder, almost like a cosmic barometer, sensitive to the sun's tantrums. This isn't just passive weathering, it's a dynamic dance where a feature we thought was static might actually be breathing in sync with forces 93 million miles away. The mechanics are mind-bending. As solar wind particles collide with Jupiter's magnetic shield, they don't just create pretty lights, they inject energy into the upper atmosphere, triggering waves that ripple toward the equator. These waves could act like atmospheric refrigerators, redistributing heat in ways that leave behind pockets of extreme cold. Picture blowing across a steaming cup of coffee. Your breath doesn't just cool the surface, it creates currents that stir the liquid beneath. On Jupiter, solar wind might be that breath, stirring the atmosphere's depths to carve out the cold spot's icy imprint. Yet for all its elegance, this theory has cracks. If solar wind drives the cold spot's behavior, why doesn't it vanish during periods of low solar activity? Historical data shows the spot has endured through solar minimums and maximums alike, its core chill unfazed by the sun's mood swings. Some researchers argue this points to a hybrid origin. Solar wind might tweak the spot's edges, but something deeper, perhaps Jupiter's own magnetic fury or hidden atmospheric waves, anchors its permanence. It's like a tree bending in the wind. The gusts might sway its branches, but the roots hold firm. The debate gets thornier when we compare Jupiter to other gas giants. Saturn, for instance, basks in the same solar wind, yet it has no cold spot equivalent. This suggests Jupiter's unique magnetic field, 20,000 times stronger than Earth's, might be amplifying the solar wind's impact in ways other planets can't replicate. Or perhaps the cold spot isn't just a product of external forces, but a rare resonance between the solar wind and Jupiter's internal dynamics, a celestial harmony that turns incoming chaos into structured cold. One thing's certain: if the solar wind really is puppeteering part of the cold spot's behavior, it's a game changer, not just for Jupiter, but for how we understand space weather's reach. Imagine distant exoplanets buffeted by their stars' winds, hiding similar cold anomalies in their atmospheres. The cold spot might be teaching us a universal language, one where sun and planet whisper secrets through the medium of frozen sky. And until we decode that language, every gust of solar wind, every flicker in the cold spot's chill, is a clue waiting to be read. Spectroscopy doesn't just reveal temperatures, it tells stories. When scientists trained their instruments on Jupiter's great cold spot, they didn't just see a dip in the heat, they uncovered a chemical fingerprint unlike anywhere else on the planet. The air here isn't just cold, it's different, laced with molecules that shouldn't exist in such concentrations at this altitude. It's as if someone took a slice of Jupiter's upper atmosphere and ran it through a cosmic chemistry set, tweaking the recipe until something entirely new emerged. Take hydrogen cyanide, for instance. This toxic compound, lethal to most earthly life, shows up in oddly high amounts around the cold spot, far more than in surrounding regions. Then there's acetylene, a hydrocarbon that's usually broken apart by sunlight at these heights, yet here it lingers like an uninvited guest. These aren't random contaminants, they're clues. Hydrogen cyanide, in particular, is a notorious energy absorber, capable of sucking up thermal radiation and irradiating it away as infrared light. Could it be acting as a natural coolant, helping to maintain the cold spot's deep freeze? It's like finding antifreeze in a glacier, a substance that actively preserves the chill rather than disrupting it. But the plot thickens with the presence of ionized molecules, fragments of gas stripped of electrons by Jupiter's relentless radiation. These charged particles are the wild cards of atmospheric chemistry, sparking reactions that neutral compounds can't. Some researchers speculate they might be the architects of the cold spot stability, forming temporary molecular nets that trap cold air in place. Picture a spiderweb woven from magnetism and chemistry, its strands invisible but strong enough to resist Jupiter's turbulence. If true, it would mean the cold spot isn't just a weather pattern, it's a self-sustaining chemical engine, constantly rebuilding its own walls against the chaos. The real head-scratcher, though, is the lack of water vapor. Jupiter's atmosphere is drenched in water, yet the cold spot shows a striking deficit, as if someone wrung out the air here like a wet towel. Water is a powerhouse for trapping heat, so its absence might explain why this region stays so cold. But why is it missing? One theory points to photodissociation sunlight blasting water molecules apart before they can accumulate. Another suggests downdrafts of dry air from higher altitudes, like a planetary scale rain shadow where moisture simply can't take hold. Then there's the helium factor. Jupiter's atmosphere is roughly a quarter helium by mass, but in the cold spot, it behaves oddly. Under extreme cold and pressure, helium can separate from hydrogen like oil from water, forming microscopic droplets that act like thermal ball bearings, rolling heat away from the area. This helium rain phenomenon is hypothetical elsewhere on Jupiter, but the cold spot's conditions might make it a reality here, a hidden precipitation that chills the air from within. Decoding this chemical cocktail isn't just academic. If certain molecules are acting as coolants, we might find similar ingredients on exoplanets with unexplained cold zones. Or if ionized gases really can stabilize atmospheric features, it could reshape how we model weather on gas giants light years away. The cold spot's chemistry isn't just a quirk, it's a laboratory, one that could rewrite the rules of planetary atmospheres. And until we crack its code, every odd molecule, every missing compound, is a breadcrumb leading us deeper into the mystery. Is the great cold spot fading into oblivion, or is it holding its ground against Jupiter's relentless atmospheric fury? The answer isn't just about size, it's a window into whether we're witnessing a cosmic ephemeron or something more enduring. Infrared snapshots spanning nearly 2 decades reveal a tantalizing pattern. The cold spot's edges appear to flicker, sometimes contracting by as much as 10% before rebounding, like a living thing breathing in Jupiter's toxic skies. But here's the twist: while its outline wavers, the core chill remains stubbornly consistent, locked in a deep freeze that defies the planet's chaos. This isn't like watching the great red spot slowly shrink over centuries. The cold spot's dance is subtler, more enigmatic. Some researchers argue the fluctuations match periods of heightened solar wind activity, as if charged particles from the sun are sculpting its boundaries. Others see parallels with Jupiter's auroral cycles, suggesting magnetic tides might be squeezing the spot like an invisible hand. Then there's the wild card: atmospheric waves from deep storms, rippling upward to buffet the cold spot's edges without disrupting its heart. It's a celestial tug of war between forces we're only beginning to map. The stakes couldn't be higher. If the cold spot is genuinely shrinking, it might mean Jupiter's upper atmosphere is undergoing a shift, perhaps a rearrangement of jet streams or a weakening of the auroral energy that some theories link to its existence. But if it's holding steady, that stability becomes its own mystery. Earth's climate features evolve over decades. Jupiter's timescale should be far grander. A spot that neither grows nor fades on human timescales hints at mechanisms we've never accounted for: hidden energy sinks, self-replenishing currents, or even feedback loops where the cold itself generates conditions to sustain itself. The most compelling clue comes from thermal maps. While optical telescopes see nothing, infrared sensors detect faint heat signatures around the cold spot's periphery, wispy tendrils that might represent energy bleeding away or fresh cold air being drawn in. It's akin to spotting the ripples around a stone dropped in water, evidence of forces in motion. Future missions with higher resolution instruments could settle the debate, revealing whether these ripples are the death throes of a fading anomaly or the breath of something far more resilient. For now, the cold spot keeps its secrets. Whether it's shrinking, stable, or something in between, one thing's clear: its very persistence, or lack thereof, is teaching us that gas giants don't follow tidy rules. They're laboratories of extremes where the ordinary becomes extraordinary, and the impossible becomes just another Tuesday. And until we crack this puzzle, every flicker, every subtle contraction is a whisper from Jupiter's hidden playbook, a reminder that some of the universe's greatest lessons come from watching how things vanish or how they refuse to. Jupiter's great cold spot and Earth's climate might seem like cosmic strangers, one a frigid enigma on a gas giant, the other a web of delicate systems on our rocky world. But peel back the layers and you'll find a surprising truth. The physics governing both aren't as different as you'd think. The cold spot's defiance of Jupiter's atmospheric norms mirrors the way Earth's own climate systems occasionally throw us curveballs, unpredictable hurricanes, lingering heat domes, or polar vortices that spill into temperate zones. Both planets, it turns out, are laboratories for chaos, and the cold spot might just hold clues to understanding our own weather's wildest behaviors. Take atmospheric stability. For decades, climate scientists assumed Earth's jet streams and ocean currents followed reliable patterns until they didn't. The polar vortex destabilizations of 2014 and 2019, which sent Arctic air cascading into North America, were wake-up calls. Similarly, the cold spot laughs at Jupiter's rules, persisting in a realm where nothing should stay undisturbed. Both cases reveal a shared truth. Stability isn't guaranteed, even in systems we think we understand. The cold spot's resilience against Jupiter's turbulence suggests there are hidden mechanisms, perhaps magnetic fields or deep atmospheric waves, that can anchor anomalies longer than models predict. If similar forces operate on Earth, even subtly, they could explain why some weather extremes linger while others vanish overnight. Then there's energy transfer. Jupiter's cold spot is a masterclass in how heat doesn't always distribute evenly. Some pockets stay frozen while others simmer, a phenomenon Earth knows too well. Consider the warming holes discovered in parts of the U.S. southeast, where temperatures have barely risen despite global trends, or the chilling paradox of Europe potentially cooling as the Arctic warms, thanks to disrupted ocean currents. The cold spot's existence proves that planets don't just passively absorb and radiate energy, they compartmentalize it, trap it, or redirect it in ways that defy averages. Recognizing this could refine how we model Earth's climate tipping points, from collapsing ice sheets to sudden methane releases, the most tantalizing parallel. Feedback loops. Jupiter's cold spot might sustain itself through a self-reinforcing cycle where cold begets more cold, a concept eerily familiar to climatologists. On Earth, melting Arctic ice reduces reflectivity, absorbing more heat and accelerating further melting. On Jupiter, the cold spot's chill could be locking in its own longevity through chemistry or magnetism, a planetary scale echo of our own climate's vicious cycles. Understanding one could illuminate the other, revealing universal principles about how systems, whether terrestrial or Jovian, tip into new equilibriums. This isn't just academic. If Jupiter's atmospheric quirks can sharpen our earthly models, the reverse might also be true. Techniques developed to track our planet's subtle energy flows like LiDAR or satellite-based heat mapping could be adapted to dissect the cold spot's secrets. It's a two-way street. The more we learn about extremes elsewhere, the better we grasp our own. And in an era of escalating weather disasters, that knowledge isn't just power, it's survival. The cold spot isn't merely a Jovian oddity. It's a mirror reflecting truths about all planets, including the one we call home. The idea that Jupiter's great cold spot might be some kind of alien megastructure or interdimensional rift makes for thrilling sci-fi. But science has a way of turning even the wildest cosmic mysteries into something far more fascinating. Sure, it's fun to imagine the spot as a frozen stargate or the footprint of some ancient extraterrestrial engine, but the reality, It's stranger than fiction, and we don't need to invent anything to make it compelling. Take the alien artifact theory. Some speculate the cold spot's unnatural stability hints at intelligent design, a cosmic refrigerator left running by some advanced civilization. But here's the catch: nature doesn't need aliens to build impossibilities. Look at Earth's own oddities, like the hexagonal storm at Saturn's North Pole or the lava lakes of Jupiter's moon Io. The universe is full of self-assembling wonders, and the cold spot fits right in. Its persistence isn't proof of engineers, it's evidence of physics we're still unraveling. Then there's the portal myth, the idea that the cold spot might be a tear in spacetime, a wormhole to some distant corner of the cosmos. It's a romantic notion, but the laws of thermodynamics shut it down fast. Wormholes, if they exist, would radiate immense energy, not cold. The spot's chill comes from absence, not some exotic distortion. Real portals would sizzle. This thing freezes. The truth: Jupiter's atmosphere is a playground for extreme physics, and the cold spot is just one more experiment nature's running without our help. The most persistent misconception, though, is that the cold spot is a storm. It's an easy mistake. Jupiter's a world of swirling tempests, so why not another one? But storms churn, they spin, they're hungry for energy. The cold spot does none of that. It's a stagnant pool of frigid air, a dead zone in a sky of violence. Calling it a storm is like calling a glacier a thundercloud. The distinction matters because mislabeling it could steer research down blind alleys. If we treat it like a storm, we'll hunt for wind patterns that don't exist, missing the real clues hidden in its stillness. Dispelling these myths isn't just about accuracy, it's about wonder. The cold spot doesn't need aliens or magic to be jaw-dropping. Its very existence challenges textbooks, proving that gas giants harbor secrets no one predicted. When we strip away the fiction, we're left with a mystery that's even richer, a phenomenon that defies models, resists chaos, and might just hold the key to understanding atmospheres across the galaxy. And that's a story worth telling straight. Why should a frigid patch of Jupiter's atmosphere matter to anyone without a telescope or a PhD? The answer isn't just written in scientific journals, it's woven into the fabric of human progress itself. Every cosmic oddity, like the Great Cold Spot, acts as a catalyst, sparking innovations that ripple far beyond astronomy. Think about it. The technology developed to study Jupiter's upper atmosphere has trickled down into weather satellites that save lives during hurricanes, while the algorithms parsing its infrared signatures now help doctors detect tumors in medical scans. The tools we forge to explore the unknown rarely stay confined to their original purpose. They reshape our world in ways we never anticipate. But the cold spot's true power lies in its ability to ignite imaginations. Picture a teenager staring up at Jupiter through a backyard telescope, knowing that beneath those swirling clouds hides a mystery defying every textbook. That moment of wonder might steer them toward a career in science, engineering, or technology fields that will define humanity's future. The Voyager missions of the 70s inspired an entire generation of aerospace engineers, and today's puzzles could fuel tomorrow's breakthroughs. When we invest in unraveling cosmic enigmas, we're not just buying data, we're planting seeds for innovations we can't yet name. This anomaly also serves as a humbling reminder of how much we still don't understand. In an era where algorithms predict our shopping habits and AI generates poetry, Jupiter's stubborn cold patch laughs at our arrogance. It's a cosmic check on humanity's hubris, proving there are still phenomena that make supercomputers stutter and Nobel laureates scratch their heads. That tension between knowledge and mystery is what drives science forward. The moment we stop being baffled is the moment we stop discovering. Perhaps most importantly, the cold spot represents a shared challenge that transcends borders. Unlike Earth's political divisions, Jupiter's mysteries belong to no nation. They're puzzles for the entire species to solve together. The international collaboration behind its discovery involved researchers from 3 continents sharing data across time zones and languages, united by pure curiosity. In a fractured world, that rare unity reminds us of what humanity can achieve when we focus on collective wonder rather than terrestrial squabbles. The next time someone asks why a cold spot on Jupiter matters, tell them this: it's not about the anomaly itself, but what it reveals about us. Our hunger to explain the inexplicable, our knack for turning questions into tools, and our capacity to unite under the banner of discovery. The universe isn't just stranger than we imagine. It's an endless wellspring of challenges designed to make us smarter, more creative, and more connected. And as long as places like the Great Cold Spot keep defying expectations, humanity will have reasons to keep looking up and pushing forward. Imagine trying to reconstruct a storm by watching only the ripples it leaves on a pond. That's the challenge scientists face when modeling Jupiter's Great Cold Spot. Cutting-edge 3D simulations attempt to bring this atmospheric enigma to life, rendering its invisible chill in vivid detail. But there's a catch. These digital replicas are only as accurate as the data fueling them. Even the most powerful supercomputers stumble when fed incomplete or ambiguous inputs, like trying to solve a jigsaw puzzle with half the pieces missing. That's where an unlikely ally enters the scene: the global community of amateur astronomers and space enthusiasts, whose collective eyes might hold the key to refining these models. Citizen science projects like Zooniverse's Jupiter Jet Hunt have already proven the public's power to spot planetary oddities that algorithms miss. Volunteers sifting through telescope images have flagged jet stream shifts and storm clusters that professional astronomers later verified. Now, researchers are exploring whether crowd-sourced observations could help map the cold spot's subtle fluctuations over time. Imagine thousands of backyard astronomers worldwide training their lenses on Jupiter, logging tiny temperature variations or boundary shifts in the spot's ghostly outline. Individually, these notes might seem insignificant, but pooled together, they could reveal patterns no single observatory could detect. It's like assembling a cosmic detective squad, where every participant adds a brushstroke to the bigger picture. The beauty of this approach lies in its scalability. While professional telescopes like Hubble or JWST offer unparalleled resolution, their observing time is fiercely competitive. Researchers might get only a few precious hours per year to study the cold spot. Amateur astronomers, though, can monitor Jupiter relentlessly, capturing its atmosphere in all its moods. Modern consumer-grade telescopes, paired with sensitive infrared filters, are now capable of detecting thermal anomalies that would have been invisible a decade ago. When these scattered observations are fed into AI-driven analysis tools, they could fill critical gaps in the models, helping scientists distinguish between fleeting noise and meaningful trends. But the real game changer, adaptive modeling. Some teams are experimenting with live simulations that update in near real time, ingesting fresh data from both professionals and amateurs to tweak their parameters on the fly. Picture a weather forecast that evolves by the hour, except instead of predicting rain, it's unraveling the physics of a planetary scale icebox. If a volunteer in Chile notices an unusual shimmer at the cold spot's edge, that anomaly could prompt the model to test new variables, perhaps a surge in solar wind or a ripple from Jupiter's auroras, adjusting its virtual atmosphere like a chef fine-tuning a recipe. This isn't just about outsourcing labor, it's about democratizing discovery. The cold spot's mystery belongs to everyone, and cracking it could require perspectives as diverse as the planet itself. A teacher in Norway, a student in Kenya, or a retired engineer in Japan might spot the clue that professionals overlook, proving that exploration isn't confined to ivory towers or space agencies. The next breakthrough might not come from a billion-dollar probe, but from a curious mind halfway across the world, peering through a telescope and wondering, what if? In the end, solving Jupiter's coldest riddle could hinge on the simplest truth. Sometimes the universe hides its secrets in plain sight, waiting for enough eyes to finally see them. Jupiter's great cold spot isn't just a passive bystander in the planet's chaotic atmosphere. It might be an active player in shaping the brutal space weather swirling around the gas giant. While we often think of space weather as solar flares and radiation storms from the sun, Jupiter's own magnetic maelstrom generates its own version, with consequences far beyond its cloud tops. The cold spot lurking in the upper atmosphere could be a hidden conductor in this cosmic orchestra, redirecting charged particles and tweaking the planet's already lethal radiation belts in ways we're only beginning to grasp. Here's the twist. Jupiter's radiation belts are some of the most violent in the solar system, packed with electrons and ions accelerated to nearly the speed of light. These belts aren't just scientific curiosities, they're death zones for spacecraft capable of frying electronics in hours. Missions like Juno have to tiptoe around them, and future probes aiming for Europa or Ganymede will need every advantage to survive. That's where the cold spot comes in. Its frigid, high-altitude perch intersects with the fringes of these radiation belts, and its unique properties might be acting like a cosmic baffle, scattering particles or even creating temporary safe zones. Imagine a mountain disrupting jet streams on Earth, except here, the mountain is made of cold, thin air, and the streams are rivers of radiation that could make or break a billion-dollar mission. But how? One theory suggests the cold spot's temperature anomaly alters the conductivity of the ionosphere, the layer of charged particles at the top of Jupiter's atmosphere. Changes in conductivity could reshape how magnetic field lines guide radiation, potentially funneling particles away from certain regions or intensifying them in others. It's like a traffic cop for cosmic rays, redirecting them along unseen highways. Data from Juno hints at strange kinks in Jupiter's magnetic field near the cold spot's longitude, as if the spot's presence is warping the invisible forces around it. If confirmed, this would mean the cold spot isn't just a weather feature. It's a space weather engine with tendrils reaching hundreds of miles into the magnetosphere. The implications for exploration are staggering. Europa, with its subsurface ocean, is one of the most promising places to hunt for extraterrestrial life, but its orbit plunges it right through Jupiter's radiation hellscape. A better understanding of the cold spot's influence could help mission planners time flybys or even identify radiation shadows where spacecraft might linger with less risk. It's not just about shielding, it's about strategy. If the cold spot's effects are predictable, future orbiters could use its fluctuations like sailors riding tidal currents, slipping through gaps in the radiation onslaught. Yet the cold spot's reach might extend even farther. Jupiter's magnetosphere is so vast that if it glowed visible, it would appear larger than the full moon in Earth's sky. This colossal bubble of magnetism interacts with the solar wind, sometimes deflecting it, sometimes swallowing it whole. The cold spot, by tweaking the ionosphere, could be subtly altering how Jupiter's magnetosphere breathes, influencing how much solar energy penetrates the system. On Earth, such interactions drive auroras and satellite disruptions. On Jupiter, the stakes are magnified 1,000-fold. A flicker in the cold spot's stability might ripple outward, changing how radiation bathes the moons or how auroras flare at the poles. This isn't just about one planet. The lessons learned here could apply to exoplanets with fierce magnetic fields, worlds where radiation might make or break the possibility of life. If a cold spot on Jupiter can reshape space weather, what might similar features do elsewhere in the galaxy? The cold spot is more than a puzzle, it's a key, one that could unlock secrets about how planets armor themselves against the cosmos and how we might someday navigate their lethal beauty. Could the great cold spot blink out of existence overnight, vanishing like a snuffed candle in Jupiter's turbulent sky? Unlike the great red spot, whose slow decline has unfolded over centuries, this icy anomaly operates on a different clock, one that could stop ticking at any moment without warning. The terrifying beauty of studying Jupiter is that nothing is guaranteed. Storms that rage for decades can dissolve in months, and atmospheric features that seem permanent might be far more fragile than they appear. If the cold spot suddenly disappeared, it wouldn't just leave scientists stunned, it would force them to rewrite entire chapters of planetary science. The stakes are high because the cold spot's very existence defies our current models. If it vanished, it could mean one of two things. Either the forces sustaining it were far more delicate than we imagined, or something catastrophic shifted in Jupiter's hidden atmospheric machinery. Imagine a skyscraper standing defiantly in a hurricane. If it collapses, was the storm too strong, or did the building's foundation have a flaw we never noticed? The cold spot's disappearance would be that collapse, a cosmic stress test revealing which of our theories hold weight and which crumble under scrutiny. But here's the twist: its potential fragility might be its greatest lesson. Most of Jupiter's weather operates on scales that dwarf human lifetimes, but the cold spot could be a rare exception, a feature balanced on a knife's edge. If it's tied to Jupiter's auroras or magnetic field fluctuations, a sudden surge in solar wind or a shift in Eo's volcanic activity might disrupt the delicate equilibrium keeping it alive. Unlike the Great Red Spot, which is a self-sustaining engine of chaos, the cold spot could be a house of cards, reliant on perfect conditions to maintain its icy grip. Yet its resilience would be just as revealing. Every year it survives is another clue that our understanding of atmospheric stability is incomplete. Earth's climate has tipping points, thresholds where small changes trigger irreversible shifts. Could Jupiter have them too? If the cold spot endures despite solar storms, seasonal changes, and internal upheaval, it might point to feedback loops or hidden anchors we've yet to discover. The longer it lasts, the more it hints at deeper, invisible forces at work, like a clock that keeps perfect time despite being thrown into a storm. The only way to know is relentless observation. Missions like Juno and JUICE are our eyes in the sky, but they can't watch forever. The cold spot might fade tomorrow, or it might outlive every probe we send. That uncertainty is what makes it so thrilling. In a universe where cosmic events often unfold too slowly for human patience, here's a mystery that could change in the blink of an eye. Whether it vanishes or persists, the cold spot won't go quietly. It'll leave behind clues, questions, and maybe even a new blueprint for how gas giants whisper their secrets to those willing to wait and watch. Jupiter's great cold spot isn't just a local oddity. It's a blueprint for decoding atmospheres light years away. Across the galaxy, telescopes have spotted hundreds of hot Jupiters, gas giants roasting close to their stars, and colder cousins lurking in the shadows of distant solar systems. Many likely harbor atmospheric quirks just as bizarre as Jupiter's icy enigma, but spotting them requires knowing where and how to look. That's where the cold spot becomes more than a curiosity. It's a training ground, teaching us what signatures to hunt for in the flickering starlight filtering through alien skies. Consider the challenge when studying exoplanets. Astronomers don't get crisp images of swirling clouds or raging storms. Instead, they piece together atmospheric clues from spectral lines, the chemical fingerprints left when a planet passes in front of its star. Normally, these observations focus on heat. Hotspots, glowing methane, or searing winds leave bold marks in the data. But the cold spot reveals something revolutionary. Sometimes the most telling features aren't the brightest but the darkest. Its infrared shadow, a temperature dip against Jupiter's warmer backdrop, proves that cold anomalies can be just as distinctive as fiery ones. Future telescopes like the European Extremely Large Telescope, with its unprecedented sensitivity, might catch similar negative spaces in exoplanet atmospheres, revealing hidden structures no one thought to search for. The cold spot also rewrites expectations about stability. Before its discovery, most models assumed gas giant atmospheres would smooth out extremes over time, like cream swirling into coffee. Yet here's a feature that defies erosion, surviving centuries in a maelstrom where even titanic storms dissolve. This forces astronomers to reconsider what's possible on distant worlds. An exoplanet with puzzling temperature inconsistencies. Instead of dismissing them as instrument error, scientists might now ask, could this be a permanent cold vortex, a Jupiter-like anomaly clinging to existence against all odds? The very presence of the cold spot expands the menu of what we consider normal for gas giants, and that shift in perspective could lead to breakthroughs when interpreting baffling exoplanet data. Perhaps most crucially, Jupiter's anomaly teaches us to expect the unexpected. Before the cold spot, no model predicted a stable, ultra-cold region in a gas giant's upper atmosphere. Now that we know such features exist, it's a reminder that exoplanets free from the constraints of our limited solar system might harbor even wilder atmospheric tricks. Imagine a world with multiple cold spots arranged like celestial crop circles, or a reverse Jupiter, where the poles are hotter than the equator. The cold spot is a masterclass in cosmic humility, proving that nature's creativity outstrips even our boldest theories. Every time we encounter an atmospheric rule on Earth or Jupiter, the universe seems to whisper, "Now break it." This isn't just academic. As we gear up to study potentially habitable moons around exoplanetary gas giants, understanding their atmospheres becomes vital. A cold spot like Jupiter's could shield underlying moons from radiation or alter local weather patterns in ways that affect surface conditions. The tools we sharpen today to dissect Jupiter's enigma might tomorrow help us pinpoint the safest or strangest places to search for life beyond our solar system. The cold spot isn't merely a Jovian quirk. It's a lantern in the dark, illuminating paths to discoveries we haven't even dreamed of yet. Even after years of observations, Jupiter's great cold spot remains a cosmic riddle wrapped in layers of frozen mystery. The most baffling question isn't just why it exists, but how something so fragile persists in an atmosphere that shreds storms like tissue paper. Conventional physics suggests the spot should have evaporated centuries ago, its cold air scrambled by Jupiter's relentless turbulence. Yet here it sits, a glacier in a hurricane, defying every expectation of how energy moves through planetary atmospheres. Some researchers whisper about atmospheric superconductors, hypothetical pathways that siphon heat away with impossible efficiency. Others point to Jupiter's deeper layers, where swirling oceans of metallic hydrogen might generate unseen currents that lock the cold in place from below. The truth, we're still grasping at theories like climbers on an icy cliff, searching for handholds in the dark. Then there's the puzzle of its energy source. Most atmospheric features feed off obvious power supplies: solar radiation, internal heat, or kinetic energy from winds. But the cold spot operates differently, like a clock that runs without batteries. Could it be tapping into Jupiter's monstrous magnetic field, converting auroral energy into some kind of planetary refrigeration cycle? Or is it harvesting momentum from the planet's dizzying rotation, spinning fast enough to create a self-sustaining cold trap? The spot's eerie stability suggests an energy balance so precise it borders on artistry, a natural thermostat fine-tuned by forces we've yet to identify. Until we understand this equilibrium, every explanation feels like describing a symphony by hearing only one instrument. Perhaps the most humbling question isn't about Jupiter at all, but about us. The cold spot might not be unique. We may simply lack the tools to spot its siblings. Imagine if early astronomers had only studied Earth's tropics, never realizing deserts or polar ice existed. Our current infrared telescopes are like those first crude lenses, revealing only the most obvious anomalies. Future instruments could uncover dozens of similar cold zones, each tweaking our cosmic perspective. Already, re-examined data from the Cassini mission hints at transient cold patches in Saturn's upper atmosphere, flickering cousins to Jupiter's icy giant. If true, we're not looking at a freak occurrence, but a whole new class of atmospheric phenomena waiting to be catalogued. The deeper scientists dig, the clearer it becomes. The cold spot isn't just a curiosity. It's a mirror reflecting the gaps in our understanding of fluid dynamics, magnetism, and planetary scale energy transfer. Every time researchers think they've pinned it down, it throws another curveball, like its recent flickering episodes, where its edges pulsed in ways that matched neither auroral activity nor solar wind patterns. These anomalies aren't frustrations, they're breadcrumbs leading toward discoveries we can't yet imagine. The cold spot's greatest lesson might be that the universe always keeps a few tricks up its sleeve, ensuring the cosmic game of hide and seek never ends. And for those who study it, that's the most thrilling possibility of all. Cutting-edge technology is peeling back the layers of Jupiter's great cold spot like never before, transforming what was once a blurry infrared smudge into a high-definition cosmic puzzle. Adaptive optics systems, the unsung heroes of modern astronomy, are at the forefront of this revolution. These systems work like real-time eyeglasses for telescopes, using deformable mirrors that flex thousands of times per second to counteract Earth's atmospheric turbulence. The result, crystal-clear images that reveal the cold spot's intricate structure, swirling tendrils of frigid gas, razor-sharp boundaries defying Jupiter's chaos, and subtle pulsations that hint at hidden energy flows. At the European Southern Observatory's very large telescope, these systems have captured details as small as 200 kilometers across, equivalent to spotting a dime from 40 miles away. But the view from Earth is just the beginning. Space-based infrared telescopes like NASA James Webb Space Telescope are rewriting the rules of planetary observation. Free from our atmosphere's distorting effects, Webb's mid-infrared instrument MIRI maps the cold spot's thermal signature with jaw-dropping precision, distinguishing temperature variations finer than 5 degrees Celsius across its vast expanse. Recent scans revealed something startling. The spot isn't uniformly cold. Its core plunges to staggering lows, while the edges flicker with faint warmth, like an icy pond with thin spots where heat seeps through. These gradients are clues, suggesting the spot isn't a static slab of cold but a dynamic system with internal structure. The real game-changer, though, is spectroscopy, the art of decoding light's hidden messages. Modern spectrometers aboard observatories like the Atacama Large Millimeter Array dissect the cold spot's glow across hundreds of wavelengths, exposing chemical oddities that defy expectations. Last year, they detected an unexpected spike in phosphine gas, a molecule typically associated with Jupiter's deep, hot layers hovering right in the coldest zone. It's like finding steam rising from a glacier, a paradox that's forcing scientists to reconsider how material circulates between Jupiter's depths and its frozen upper reaches. AI is turbocharging this detective work. Machine learning algorithms sift through decades of telescopic data, spotting patterns no human could discern. One neural network, trained on simulated Jupiter atmospheres, recently flagged a peculiar rhythm. The cold spot's temperature dips slightly every 42 days, a cadence that matches oscillations in Jupiter's magnetic field. This hints at an invisible tether between the planet's electromagnetic heartbeat and its frigid anomaly, a connection that could rewrite textbooks on how energy moves through gas giants. The next wave of tools promises even greater leaps. NASA proposed Origin Space Telescope, slated for the 2030s, will pack spectrometers so sensitive they could detect a single cold molecule in a sea of warmth. Meanwhile, quantum sensors in development could map magnetic fields around the cold spot with nanometer precision, revealing whether magnetism truly is the hidden architect of this icy enigma. What makes this technological arms race so thrilling isn't just the gadgets, it's the philosophy shift they represent. For centuries, astronomy was passive. We observed, we catalogued, we theorized. Now, with adaptive optics correcting distortions in real time, AI predicting atmospheric changes before they happen, and fleets of nanosatellites providing round-the-clock monitoring, we're transitioning from spectators to participants in Jupiter's atmospheric drama. The cold spot may have dodged discovery for generations, but with these tools sharpening our vision daily, its days as a mystery are numbered, and whatever answers we uncover will likely reshape our understanding of planets far beyond our solar system. Jupiter's great cold spot might not have the crimson drama of its more famous sibling, but its quiet, unsettling presence has quietly seeped into the crevices of popular culture like a slow-moving frost. While the Great Red Spot fuels grand space operas with its swirling fury, the cold spot's eerie stillness makes it the perfect muse for stories that thrive on the uncanny tales of cosmic horror, frozen time loops, and phenomena that defy logic. In the sci-fi anthology Dark Stars, author Emily Chen reimagines the spot as a gravitational scar, a wound in space-time where a long-dead alien civilization attempted to freeze entropy itself. The spot's unchanging nature becomes a terrifying plot device, a countdown clock that never ticks, a warning from the universe that some forces are beyond human comprehension. Artists, too, have been drawn to its paradoxes. Digital sculptor Rafael Mendes's viral installation Negative Sun depicts the cold spot as a three-dimensional void hovering over Jupiter's cloud tops, a black hole's shadow rendered in glass and neon. Viewers describe walking through the exhibit and feeling an inexplicable chill, as if the artwork channels the spot's actual frigidity. Meanwhile, indie game Juno's Shadow turns the anomaly into a puzzle. Players navigate a derelict probe through the spot's dead zone, where instruments fail and time stutters, a gameplay mechanic inspired by real scientific debates about the spot's effect on spacecraft. But the cold spot's biggest cultural impact might still be ahead, with NASA's upcoming missions set to shine a spotlight on Jupiter's mysteries. Filmmakers and writers are already mining its potential. Rumors swirl that a prestige sci-fi series in development at a major studio will use the spot as the backdrop for first contact, not with aliens, but with something far stranger, an intelligence that communicates through absence and cold. And in the art world, a collective of holographic artists is planning an immersive experience that will let audiences step inside the cold spot, surrounded by projections of its infrared glow while ambient soundscapes mimic the eerie silence of its frozen heart. What makes the cold spot so compelling isn't just its science, but its symbolism. In a world obsessed with speed and noise, here's a cosmic phenomenon that embodies stillness, patience, and the quiet defiance of expectations. It's no accident that poets have begun comparing it to grief, to trauma, to the parts of the human experience that remain frozen in time while the world rages around them. The spot's cultural journey mirrors its scientific one. What starts as a curiosity becomes a mirror, reflecting back our own fascinations and fears. And as we keep unraveling its secrets, one thing's certain: it won't just inspire stories. It'll change them. Jupiter's great cold spot isn't just a puzzle, it's a cosmic wake-up call, a reminder that even in our own backyard, the universe still holds cards close to its chest. Think about it. We've mapped the surfaces of distant exoplanets, unraveled the birth cries of black holes, yet right here, swirling in the clouds of a planet we've studied for centuries, lies an atmospheric anomaly that defies every textbook. This isn't just about a cold patch on a gas giant. It's about humility. It's about recognizing that for all our telescopes and supercomputers, nature still has the power to leave us utterly bewildered. The cold spot story mirrors the very essence of scientific discovery, a dance between frustration and wonder. When astronomers first spotted its infrared shadow in 2017, it wasn't just a new feature to catalog. It was a disruption, a cosmic shrug at everything we thought we knew about atmospheric physics. Here was a structure wider than Earth, colder than anything around it, and somehow immune to Jupiter's relentless storms. Models failed, theories crumbled, and that's exactly what makes it so thrilling. Science doesn't grow when the pieces fit neatly together. It leaps forward when they don't. What's truly remarkable is how this icy enigma bridges past and future. For centuries, Jupiter's great red spot dominated our imagination, a tempest so iconic it became shorthand for planetary extremes. But the cold spot, it's the red spot's quiet, mysterious counterpart, a feature that doesn't roar but persists, whispering secrets about forces we're only beginning to grasp. As missions like JUICE and next-generation telescopes prepare to peel back its layers, we're not just solving a Jovian riddle, we're rewriting the playbook for how gas giants, and perhaps all planets, work. Consider the ripple effects. If the cold spot's stability stems from Jupiter's magnetic field or deep atmospheric waves, that knowledge could revolutionize how we interpret exoplanet data. Imagine peering at a distant hot Jupiter and realizing its strange thermal fluctuations aren't noise, they're signatures of hidden cold vortices, cousins to Jupiter's Anomaly. Or picture future probes to Europa, using cold spot-inspired models to navigate radiation belts shaped by invisible atmospheric tides. This isn't abstract science. It's the groundwork for tomorrow's breakthroughs. Yet for all its scientific weight, the cold spot's greatest gift might be intangible, reigniting that childlike awe we sometimes lose in the grind of data and deadlines. There's something profoundly human about staring at Jupiter through a telescope, knowing that hidden in its glow is a mystery that defies explanation. It's the same wonder that drove Galileo to sketch its moons, that propelled Voyager past its clouds, and that now fuels researchers hunched over flickering screens, chasing answers in pixels of infrared light. So as we wait for new missions to unveil the cold spot's secrets, let's not forget the bigger picture. Every unexplained phenomenon is an invitation to question, to explore, to marvel. Whether you're an astrophysicist running simulations or a stargazer squinting at Jupiter's pale dot from your backyard, that invitation is open. The universe isn't done surprising us. And if a single cold patch on Jupiter can upend decades of assumptions, just imagine what else is out there waiting to be discovered. the next great cosmic revelation might not come from a distant galaxy. It could be hiding in plain sight, right where we